Hey everybody, I would like to welcome back Luke Youngblood. He will be speaking about the approaches to validators, architecture and security, trust models, and slashing basics. Luke, do you just mind reintroducing yourself real quick to the new people who showed up? And yeah, take it away.
Sure, thanks Cameron. Hi everyone, my name is Luke Youngblood, and I'm the founder and CEO of Blockscale, which is my own company. In 2018, I helped the Tezos Foundation build their validator infrastructure. And then in 2019, I joined Coinbase Custody, and I currently work on launching new proof-of-stake networks for Coinbase. A big launch we did last year was the Tezos Staking Rewards Program. So I run the validators at Coinbase, and I work on a small team of engineers at Coinbase Custody. And today, I'd love to talk to you about different approaches to validator security. So as you consider launching your own validator as a service provider, these are some of the patterns you can adopt to improve the security. In my previous talk, which you might have not seen, I mentioned that in proof-of-stake networks, validators replace the raw compute power and electricity used by miners in proof-of-work. This is replaced by security and operational skills that validators need to have. So it's very important for both the security of your individual validator setup and for the security of these proof-of-stake networks as a whole, that we have highly secure validator setups. So I'm going to give you some patterns you can use to adopt those. And then also, at the end, we'll have time for questions. I'm coming to you live from my Lamborghini dealership. Not really, but it's kind of fun, I guess, to pretend. Anyway, let's get right into it. So in proof-of-stake, just a quick recap of what we talked about earlier. In proof-of-stake networks, validators provide these secure and highly available cryptographic attestations. So there's two things they mainly do. One is producing blocks that include transactions in the digital ledger, and the other one is voting on blocks that other validators have produced. And they essentially trade this raw compute power and electricity from proof of work for the security and operational skills required to provide these secure cryptographic attestations, or votes. We'll just call them votes because it's easier than saying secure cryptographic attestations. And the challenge here is that a compromise of validators with significant stake could lead to a lot of bad outcomes. It could lead to censorship of transactions. It could lead to loss of funds. It could lead to if bad actors have access to the private key material, they can manipulate votes, and they can ultimately attack these networks and perhaps try to double spend. So the goal of every validator should be to just make the cost of a successful attack higher than the value that an attacker would gain. So if you think about how much risk or how much monetary value is at stake in your validator, literally at stake. If you have $10,000 in bonds or deposits, and you can make the cost of a successful attack $1 million, you're doing pretty well, because you've essentially made the cost of attack way higher than the value that an attacker would gain. So this is basically how we secure systems that are connected to the internet. There's a lot of bad actors out there, and if the cost of an attack is lower than the value, they're going to make that attack happen. And you can see this in proof of work with some of the double spend 51% attacks that have happened on some of these smaller networks where it only costs a small amount of money to do that. So let's just review really quick the slashing mechanisms for proof of stake. These slashing mechanisms exist to protect the network from the risks of these attacks. They're not made just to be malicious. The blockchain, the asset issuers that are creating these networks are not just introducing slashing just because they can. They're doing this to solve the real world problem of how we secure these networks and how we trust the transactions in the digital ledger are valid transactions and they haven't been censored, and that they are immutable and censorship resistant. So what that means is that validators can be slashed if you vote for or produce two different blocks at the same height. This is called equivocation. If you try to vote on two different blocks, one of them that contains a transaction in it and the other one that doesn't, you will be slashed because you're essentially trying to attack the network. In some networks, the validators can also be slashed for liveness faults. So this means if you're offline for too long. You typically see this in Byzantine fault-tolerant networks like Cosmos, which we talked about earlier. In Byzantine fault-tolerant networks, 2/3 of the validators must vote on every block before it's final. So if part of the network is offline, that could cause a halt in the chain and a halt in consensus. So these networks encourage liveness by having a small slashing penalty if you're offline for too long. And then in some networks, other validators may actually earn a reward for presenting evidence of equivocation or a double signature, which effectively places a bounty on your validator security. You know, if the reward for causing a double signature is a significant amount of money, and I can easily compromise your validator and cause you to double sign, that becomes a profitable attack vector for bad actors. So because all these slashing mechanisms exist, we have to come up with ways to secure our validator and secure these networks. So I want to talk to you about this paradigm that I've noticed in operating validators. And it's really a triangle around three characteristics: availability, security, and low cost. So if you follow this paradigm, you can basically achieve two of these three things, but you cannot have all three at once. And so let's talk through what that means in the real world implications for validator setups. So there are different ways you can set up your validator. One way you might set up a validator that optimizes for security and low cost is to validate at your home or office with a Ledger device. So you can load a validator app on your Ledger. Ledger is a hardware security module that allows you to store your private key material off the computer that's running your validator software. And this is a highly secure way to validate because the private keys don't exist on your validator. So if someone hacks your validator, they're not going to be able to extract your private key material. And it's also low cost because you could probably do this with a computer you find around your home or office. But it's not very available because you're using a home or a home office internet connection. So you probably don't have large data centers and multiple internet providers. You probably don't have a backup power system. So if you get denial of service attack or someone tries to knock you offline or your internet goes down, you might have a liveness fault. So you've optimized for security and low cost, but you might have availability issues. Another way people set up validators typically, and we see this very commonly on these test nets, is to validate without HSMs or without hardware security modules in the cloud. So you can buy a very low cost cloud instance, maybe $100 a month or less, and you can set up your validator and load the private key material directly on your cloud instance. And this will give you pretty good availability because now you're in a data center, you have multiple internet providers. These internet providers do a great job of keeping your systems online, and you'll be fairly low cost. But if your validator is compromised, you're going to lose the private key material, you will be slashed, and you'll probably lose funds. So it's going to be a bad day for you if you compromise on security. And then the second way, or third way, sorry, that people set up validators is typically validating with hardware security modules in the cloud or a data center. And so in this case, you're optimizing for availability and security. You're going to pay more because you have to rent a cage in a data center, or you're renting cloud HSMs. But you're going to have high security because you have your private key material stored in a hardware security module. And you're going to be highly available because in the cloud and in a data center, you can have multiple internet providers, and the cloud provider or data center colo provider can help mitigate a lot of the denial of service attacks that you might be exposed to otherwise. So this is the way that a lot of professional validator as a service companies set up their infrastructure. This is the way we set up infrastructure for the Tezos Foundation and also for Coinbase custody. So this is the pattern that I want to focus on most, are patterns for secure and highly available validators. So I'm going to cover three main patterns that you can leverage. The first pattern is around automation and the two-person rule. So if you're able to automate the provisioning of all your validator infrastructure, there's a concept that we use called infrastructure as code. And what that means is rather than manually configuring your validator, rather than going online and logging into your server and running commands as root or using sudo, installing packages, compiling code, rather than doing all those steps manually and putting your validator at risk of human error, you do this through code. So you write code through Terraform, CloudFormation, whatever tool you want to use that provisions all the infrastructure you need to stand up validators in a fully automated way. And then you put that code in a GitHub repository, and then you put controls around the GitHub repository so that no single engineer can make changes to that code without a second person approving it. And so this is a concept that's been done in traditional finance for years, where, like at a bank, for example, maybe one employee can't access the bank vault with millions of dollars by themselves. Maybe they need a second person to turn their key and access the bank vault at the same time. So this two-person rule has been used for centuries, basically, to mitigate the risk of a single bad actor, causing loss of funds. And so if you're able to provision all of your validator infrastructure through code, and you put really tight controls around the source repository where that code exists, you can achieve this two-person rule where you always have a second set of eyes on every change made to your validator. And so this can allow you to protect the supply chain of software that leads to your validator, and this is super important. There's this quote from Elon Musk that I want to share with you. What really matters is the machine that builds the machine, the factory, and that is at least 2 orders of magnitude harder than building the vehicle itself. So what he's talking about is building the supply chain for the Tesla car. It's really hard to build a factory that can turn out cars at a rate of hundreds per week or thousands per week or whatever they build. You have to build the machine that builds the machine. It's actually harder than just building a single car. And so you should focus on building the machine that builds your validators. It'll take you longer initially, but if you can accomplish this, then you'll be able to stand up mini validators at a very rapid clip, and you'll be able to do them in a repeatable and safe way. And then you'll also be able to protect your validators from the risk of a single bad actor causing loss of funds or causing slashing. So what you see here is a diagram of the way that I've built this for the Tezos Foundation. So this is the machine that builds the Tezos Foundation validators. And you see 3 kind of swim lanes here. There's the green on the left, yellow in the middle, and red on the right. So the green swim lane is the path to get code into one of the pre-production test nets. So if I want to make a change to a validator, if I'm a developer, I want to make a change to a validator that's running on CarthageNet, for example, which is the new protocol test net, I can simply check in that infrastructure as code into the GitHub repository. And we have an automated CI system called Code Pipeline running in the cloud that's continuously looking at that branch for any changes, and will automatically detect those changes, build all the software artifacts, and then deploy them automatically across a set of infrastructure in the cloud. This all happens through automation, so there's no human involved in the loop other than the developer that pushed the code. And so there's little risk of human error, and there's also very little risk of the change not being what we expect to see happen in the code. But when I get to later environments, there might be more safety checks involved. So for example, I can go to staging branch, which is the current protocol testnet, BabylonNet. I can merge my same changes into that branch, and I can self-approve that pull request merge. And that'll automatically deploy all the changes, build all the software, and deploy it to the current protocol testnet. But when I want to go to mainnet, this is where real funds are on the line. These are not testnet tokens. I want to be really careful about what changes get introduced to my mainnet validators. And so here I'm going to implement the 2-person rule. And I'll require the code reviewers, which are other trusted individuals, maybe other software engineers on my team, maybe a director or someone that has the ability to reason about the code and look at whether what I'm doing is safe or not. So you should encourage this culture of like collaboration and code reviews, and you should have more than one person that you trust to implement changes on your validators. So if you adopt this model, you can actually hire operations staff for your validators. That operations staff can put pull requests in, and then you as the owner of your validator as a service startup can actually approve those code changes with some confidence, knowing that like one of your employees isn't going to steal money from you. You'll be able to review those changes and see whether they're secure or whether they introduce a vulnerability or some way to attack your validator. So This first concept is how you secure your software supply chain. Use a private Git repository, use infrastructure as code tools such as Terraform or CloudFormation. The tooling isn't really that important. It's just that you use a tool you're comfortable with. Require a second person to approve any changes to code before it is merged into production branches. And then build your artifacts in a secure and isolated environment from trusted sources. This is really critical. If you're building artifacts from untrusted sources, if you're piping artifacts into a shell script that runs as root, and you don't know where that came from, you could be introducing malicious code that's going to cause your validator to double sign or compromise your private key material in some way. So use trusted sources and understand where every dependency comes from. Use cloud providers such as Amazon or Google instead of CI solutions. The cloud providers have remarkably better security than some of the CI solutions like Circle CI. I don't mean to pick on Circle CI, but they just don't have the level of security that some of the cloud providers have. Don't build artifacts on your laptop. Build them on a secure cloud machine because, are you confident that your laptop isn't compromised? I'm not confident that my laptop isn't compromised. So I never build artifacts on my personal computer. I always build them in a secure build environment. And then pin all the dependencies and dependencies of those dependencies. So you're going to be bringing in both open source software from the blockchain network itself. So things like Cosmos SDK for Cosmos or the Tezos open source software, you're going to be bringing those in. So go directly to the core team's repository and pin your specific validator to a Git commit so that you don't have to worry about if their GitHub credentials get compromised and you run a malicious build. And then another interesting thought exercise is actually to think about what could my evil twin do? If tomorrow I was replaced by an evil twin version of myself, could that person cause a loss of funds? Could that person cause my validator to double sign and get slashed? And if they could, then what can I do to solve that problem? What safety checks can I put in place? What gates can I put in place? What two-person approvals could I put in place to prevent my evil twin from doing malicious things? And if you can solve those things, if you can make it so your evil twin could do no harm to your validator, you'll be in a really good place from a security standpoint. So the next concept I want to talk about is really around network and account isolation boundaries. So if we divide our validator functions into multiple compartmentalized cloud accounts or data center colos, and we have different user authentication and network boundaries, we can actually minimize the risk of a compromise. So here are some of the design implications. Systems that communicate with we're going to put all our keys in a secure key storage account, right? We're not going to keep our private key material on nodes, on validator nodes. We're going to take the private key material and we're going to put it in an HSM or generate it in an HSM in the first place. That's the better solution. And then we're going to keep those HSMs in a separate colo or data center or physical infrastructure or cloud account if you're using a cloud HSM. And we're not going to share authentication credentials between the validator account and the key storage account. So validators never have access to the account where the private key material is stored, and they never have the ability to actually export private key material. So even if your validator is compromised, it should not be able to lead to a loss of funds or loss of private keys. And so here's a high-level illustration of what that looks like. So going from left to right, the blockchain network, which is the peer-to-peer network that everyone has to participate in consensus in. Connecting to that, we have this network access layer, and that should be in a dedicated account or dedicated set of infrastructure. That can be in the cloud, and we typically see this network access layer that connects our validators to the rest of the blockchain network being in the cloud, because those cloud providers, like I mentioned earlier, can protect you from denial of service and other type of network attacks. Then you have your validator account. The validator account is an isolated account that should not have any internet access. It should only be able to peer with the validator node, or sorry, the network Sentry nodes that are running in the network access layer account. So the validator account should never talk directly to the public internet, and it should only peer with Sentry or Edge nodes that are operating in that network access layer account. And then when you need to generate votes or produce blocks and you need to sign those votes or sign those blocks with your private key material, you'll need to make requests from the validator account to the key storage account. And the key storage account is where all of your hardware security modules and your remote signers will live. And I'll talk about remote signers in a second. So remote signature generation is really what lets us isolate these things. So in early 2018, when I first started working with the Tezos Foundation, we were trying to think of creative ways we could solve this problem of validators requiring access to private key material to generate cryptographic signatures, and a compromise of a validator leading to a loss of private key material. The way we decided to solve this is by creating a piece of middleware called the remote signer. So what the remote signer does is it gets signature requests from a validator node, and then it gets a signature from the hardware security module. So it does some safety checks on the payload it's about to sign to make sure it's something we really want to sign. And then if it is something we want to sign, it returns the signature back to the validator who can propagate it to the rest of the blockchain network. And so this is what this looks like in Tezos. It's not enough to just sign any arbitrary message that we receive from the validator node, because if someone gets on this validator node and they compromise that box and they ask the remote signer to double sign, if you don't have any logic in the remote signer that prevents that, it's just as bad as kind of keeping your private key on the node. You can still double sign and you can still be slashed. So what we actually do is we inspect the payload of the transaction we're about to sign. And in Tezos, the payload is in hexadecimal bytes. In other blockchain networks, the payloads will have a different format. But what you want to do is you want to actually look at, you don't want to trust the validator that this is a legitimate message to sign. You want to actually look at the payload. What am I signing? And is this something I want to sign? Is this a staking transaction? Now, in some blockchain networks, you have a separate consensus key that's used for your validator from a spending key that's used to send funds. But in Tezos, they're the same key. So we want to make sure that this is a staking transaction and not an unauthorized funds transfer. Have we signed this block height before? If we've already signed a message at this block height, reject the signature request. We don't want to double sign. If this is a funds transfer, is the address whitelisted? Because Tezos validators have to pay their delegators. So as they receive rewards, they have to distribute those to their delegators. And so the remote signer allows us to actually whitelist all of our delegator addresses and put rate limits on how much funds we can send to them in a given day or in a given time period. So let's make sure that I'm not sending 1 million XTZ tokens to one of my delegators. Let's have a rate limit that's, you know, a reasonable amount of rewards that they would receive in a given cycle or epoch. And then also, is this a governance vote? If it's a governance vote, then I want that to go through, because governance is important, and you know, we should come up with mechanisms where we can securely vote in governance. So by inspecting the payloads of that we're about to sign, we can actually perform all these safety checks and reject signature requests that are invalid or that might potentially cause loss of funds or double signing or slashing. It's very important that we kind of keep this remote signer outside of the validator. There's a few patterns I've seen where people will have the remote signer on the validator node itself with like a ledger attached directly to the validator hardware, so the validator server, and the remote signer is literally just running as a piece of software on the validator node. That doesn't really help you, because if you can compromise that validator server and you're just running the remote signer locally, now I can remove those safety checks that are so important, and I can still double sign. So having it on a separate system is really important. Also, having this monotonically increasing high watermark. So this is how we detect whether we've signed a particular block height before or not. We have a monotonically increasing counter called a high watermark, which keeps track of what's the last block height we've signed. And if it's you know, the same, then we will reject that signature request. But where this can cause trouble is when you want to have high availability. So maybe you want to have a standby validator. So you want to have a separate hardware security module attached to that standby validator or that standby remote signer. And I do strongly encourage you to put the remote signer in a separate account in a separate data center or a separate physical system from your validator itself. But let's say you want to have 2 of those, so in case you have a hardware failure, you're not down and you're not slashed for liveness. But if you have a separate high watermark on each one of those, like you see on the right, that can be really bad, because in a failover scenario, I might not realize that I've already signed a block at that height, and that could lead to double signing during a failover scenario. And where this can be especially problematic, where we've seen most of the double signing incidents on live mainnets, has been when a validator thought their primary validator system was offline for some reason, and so they failed over to their standby, and they didn't realize that both were running at the same time. So be extra careful of this, because if you have two validator nodes running and both of them have access to a remote signer that is using a different high watermark, you will probably double sign. It will probably happen really quickly. And so that's something to watch out for. So securely generating these cryptographic signatures is key. Here's some of the key takeaways here. Private key material should never be stored on a validator. You should leverage the remote signer to securely generate those signatures in a completely separate account or colo. And then the remote signer should inspect the payload it is about to sign for safety. It should look at what I'm actually signing. Don't trust the validator. Don't let the validator send you metadata that says this is a staking transaction, you should sign it because it's safe. Look at the payload, because that's the only way you can trust it. The validator might be compromised. And then be especially careful around failover or disaster recovery scenarios to avoid situations that could cause double signing. And typically that's what I mentioned earlier, failing over to another data center, to another piece of hardware that might have a counter that's behind the current block height, or making double sure that your primary validator node is offline before you start your secondary validator node. If you actually separate out the validator from the remote signer, so you have, you can actually have two validator nodes here on the left, and you can achieve high availability because both of them will attempt to sign, but only one of them will succeed. And so in test nets, for example, we always operate two validators, both attempting to double sign at all times, so that we have confidence so that our double signing protection actually works. So that's one pattern you can use. And then the last thing I want to cover is really around highly available network peering, because targeted denial of service attacks are another way that bad actors can attack proof of stake networks. And the way they would do this is by preventing validators from broadcasting their blocks and votes to the rest of the network. They could try to censor validators' blocks to try to censor transactions. They could try to censor votes from other validators so that their votes have more weight to them. There's a lot of nefarious ways that bad actors might try to attack a network by knocking validators offline. So the design implications here are that you should build a layer of nodes that act as sentries or secure relays to sort of buffer that validator node from the public internet and minimize the risks of downtime or liveness slashing. So I'll just talk about this briefly, but basically you want to build a layer of sentry or secure relay nodes in a separate account and a separate network from your validators. And only those sentry or relay nodes should connect directly to the public peers in the network. So the validator nodes themselves should only connect to those sentry or relay nodes. And the cloud providers are ideal locations. So Amazon and Google are ideal locations for this layer, this network access layer, because they automatically prevent most of the volumetric attacks that you might be subjected to on the internet. These cloud providers have terabits of internet bandwidth, and so they're able to just absorb some of the layer 4 attacks that you might see. But they're not able to prevent layer 7 attacks or application layer attacks, simply because every application is different. Every blockchain network is different. And so if an attacker is able to come up with a unique layer 7 attack that can knock validators offline, that's always a risk. And so that's something the cloud provider alone cannot protect you from. So another thing that can help prevent, let's say there was a layer 7 issue that caused attackers to be able to denial of service your sentry nodes. You should consider establishing direct peering with other trustworthy validators, maybe even in private networks, to help the network remain resilient during, and block protection could continue during an attack like that. So if you find other high security, trustworthy validators in the community, folks like Certus One that are presenting here, I'm sure they would welcome peering with you to help improve the overall peering connectivity of the network. Because ultimately, if we have a lot of trustworthy validators that are peering with each other, even if the internet itself is a mess and there's a lot of bad actors attacking the public peering on the internet, block production can still continue and the blockchain network can still function in the face of targeted and coordinated attacks across multiple validators. So consider establishing the direct peering relationship. It will help the networks become more secure, and it will help your validator remain operational even during targeted attacks. So I want to cover, just to finish with, a brief overview of the Tezos Foundation staking architecture, just so you can kind of see how we've implemented a lot of these controls in the real world. This is very high level, and this is only representing one of 4 cloud regions. So this is Ireland. We also have Frankfurt, Singapore, and Japan, because the Tezos Foundation wanted to be sure that even if Ireland or one of the cloud regions was having a bad internet day or was the subject of targeted denial of service attacks, the Tezos network could continue functioning. So it would take a pretty targeted denial of service attack to knock out 4 different cloud regions simultaneously. And then we have private peering as well across those regions. But let's take this from left to right. Starting at the key storage account. So this is a dedicated account on the left here where we have cloud HSMs that are storing the private key material. And the remote signers run in front of those cloud HSMs in this account. So this account has separate credentials that require multiple people, multiple trusted principals at the Tezos Foundation to actually access this account. So it's not something I can just access on my own if I want to make a change to it. But because the remote signer is a very thin piece of software, it's a very light piece of middleware, it doesn't need to change very often. And so we only really need to access this account once every few months, and we do this in a trusted, like a multi-party type of access scenario. And then the validators themselves that run in a validator account are able to make signature requests across a private API gateway connection called Private Link, so that they don't even have direct network access to the key storage account. They're just making API requests across this private API gateway. And the remote signer inside this key storage account does all those safety checks we talked about, and then is able to generate the signature if it's a valid staking transaction. Now, the validators need to peer with the secure relays that connect them to the rest of the network. So those exist in a separate account. Validator account has no internet access, but it peers with the secure relays that are exposed to the public internet. And then connecting out to the public internet and the rest of the blockchain network, we leverage AWS Shield Advanced, which is an advanced denial of service protection service. That's quite a mouthful. But even if you are not paying for Shield Advanced, just by being in the cloud, you get access to like Shield Basic, which protects you from volumetric attacks. Shield Advanced is an additional service that gives you access to a DDoS rapid response team. You probably don't need it, but for the Tezos Foundation, they wanted to make sure they had access to the team in case they ever got a targeted attack. They would have engineers 24/7 on standby, ready to assist them with mitigation of the denial of service. And then we have intrusion detection and prevention across all of these accounts through guard duty. And then we send all of the API access and configuration changes that are made are logged and audited in CloudTrail and sent to a separate account. Just to answer your questions, yes, the slides, I will share these slide decks out with people after the conference, and I think these sessions are recorded as well, so you can watch it later. You know, this has been a brief window into how we've set up security at the Tezos Foundation, and also some of the 3 patterns you can implement to kind of protect your validator. And I strongly encourage you to adopt these, even if you don't have the resources of the Tezos Foundation. You can adopt these practices at a much lower scale. You don't have to be in 4 cloud regions. You can be in a single data center and still remain highly secure, or a single cloud provider and still maintain your level of security. You just need to adopt these patterns of, you know, account and network isolation, secure remote signature generation, and protecting your network access layer from denial of service attacks. So with that, what I want to do is kind of open it up for questions and let everyone ask the questions you'd like to ask. I'm sure you got a lot of them. And let me try to scroll up a little bit to see if there were questions that were asked while I was talking. Is Remote Signer open source? Yes. The Remote Signer that we created for the Tezos Foundation is open sourced under an MIT license, so it's a permissible license. And I can send the link. Actually, let me put that link right in the. I believe that's the link to it. I'll put it right in the chat there. So feel free to use that if you're validating on Tezos. And then there's a couple other open source implementations of remote signer as well. Polychain Labs has created a really nice one that's written in Golang that I rather like, has some more features than mine does. Let's see, what other questions? Yeah, you need a proper protocol to handle standby since fail cases and bugs can cause slashing. This is a really important point that someone just made in the channel, Madhukar Kari. You, as a validator, you should really come up with runbooks for these type of procedures. Like have a runbook for what happens when a validator fails, or have a runbook for deploying new releases of the validator node software to your nodes, both the Sentry nodes and your validator node. Have runbooks for these processes, or do them through automation, and that way you can have confidence that you're not going to double sign in one of these events. Because the reality is, we talk a lot about bad actors, and I think most of the slashing events, this is just my educated guess, but most of the slashing events have actually not been caused by bad actors, but they've been caused by human error. The typical scenario is I thought my validator was offline, so I started my standby node, and whoops, I double signed. It happens to very large validators on the Tezos network and Cosmos and others, and they're typically due to human error. So if you have a well-defined runbook and you've tested edge cases, you should try to make it humanly impossible to double sign. Make it so that only one validator can run at a time, or make it so that there's no way your remote signer can sign a block height, even if I started my standby validator accidentally. Yeah, I'm going to upload the slides later. Let's see, let me scroll down and find some more questions. Yes, are you still working for the Tezos Foundation? Yeah, so Coinbase still lets me maintain the Tezos Foundation validators in my free time. So basically I spend a few hours every Saturday just working on Tezos Foundation related work. So it's been really nice that Coinbase has allowed me to continue in that role. I have a couple employees and contractors that work for Blockscale that help me to maintain that 2-person role. And yeah, we have a support agreement so that I can maintain like the high availability of the Tezos Foundation validators as well. Pretty much everything is so automated with Tezos Foundation that a validator can go down and will typically be automatically replaced, and I'll just get a PagerDuty alert letting me know that we're missing some votes while the validator is replaced. And then typically I just need to log on, and about 20 minutes later, the replacement validator will be online and signing votes. So most everything is fully automated, and then we really have, I use I pin every build of the software to a specific Git commit of the upstream repositories, so that when the core teams, Cryptium Labs and Nomadic Labs that develop software for Tezos release new versions of the mainnet code, for example, I pin my build pipeline to a specific commit of theirs, and then I build the artifacts in a secure build environment that get deployed automatically to validators and to the edge nodes or Sentry nodes automatically through code pipeline and code builds. That's the machine that builds the machines that I showed earlier. And so the only times we typically have outages is when our validator has a hardware failure, so it'll get replaced automatically by auto-scaling. We've had a couple hardware security module or HSM outages, but the HSM itself gets replaced. There's a cluster of those in each region. So the HSM itself gets replaced by Amazon. And then one thing that's kind of interesting is we've set up a separate, like the Cloud HSM has a separate authentication and authorization layer. So this is kind of important because we don't actually, like a compromise of your cloud account could lead to loss of funds if they can generate signatures with access to your cloud credentials. So what we've essentially done with the Cloud HSMs is we generated credentials for those cryptographic users that can actually generate signatures in an offline way, and we don't store those in an online system. So that way, there's no way that someone that has a cloud credential can actually access the private key material or export it from the HSMs themselves. They would actually have to have like the offline root password, which is itself encrypted and sharded and stored in physical vaults to actually export the private key material. And you also have to think of ways you can actually back up and protect the private key material. This is also a hard problem. So if you're using like a ledger, the seed phrase from your ledger is essentially the backup of your private key material. So you should store that offline and maybe even tear the little piece of paper in half and put half of it in a different place from the other half so that no one has access to it. No single person has access to it. There's all kinds of things you have to think about in terms of protecting your private key material, not only from risk of loss if your HSM fails, but from risk of risk of compromise by humans in the real world. Let's see, what was the Golang remote signer called? So the Golang remote signer is created by Polychain Labs. If you find their GitHub repository, or maybe it's GitLab repository, I can send a link to it. You can try to find that. But it's created by Polychain Labs. Thank you. Chad provided a link in the channel. Let's see. To examine proof of stake networks that essentially use SGX as an HSM for certain private keys needed to run the node. Do you have thoughts on this approach? Yeah, I do have some thoughts on that. SGX is a secure enclave that exists on your Intel CPU, on certain Intel CPUs that allow you to kind of do trusted compute in a secure environment. And the idea is that even if I gain physical access to the computer, I should not be able to extract key material from that secure enclave. And I should be able to only run trusted code in that secure enclave. So you could potentially run the remote signer code that does the safety checks in the secure enclave. One thing I will say, though, is that there have been a number of vulnerabilities found in SGX over the years. And so I'm not sure I trust it completely as a secure enclave. If there's an attack found on the secure enclave, there might be, the only way to mitigate it might be to buy new hardware or to buy a newer version of SGX. So I'm not quite sure I'm ready to trust it. I definitely prefer HSMs that are separate from the actual computer itself or the server itself. So that could be something like a UB HSM that runs that's attached to like a USB port on the server, or a ledger. I prefer to have the HSM actually be like physically separate from the actual validator server itself, so that if there is an Intel bug, I don't have a risk of loss of private key material. Is it possible to earn interest of staking Tezos without being a validator? Yes, for my private ledger. Yes, so Tezos has a wallet app. They have two ledger applications. They have a staking app or a baking app, which is used for validators to actually vote and participate in consensus. So this app runs continuously, and you actually leave it loaded on the ledger, and it can continuously sign votes. If you're just a holder of Tezos, you don't want to actually run a validator, you can just use the Tezos wallet app to delegate to a validator, and then they will be able to stake on your behalf, and they will be able to vote for you, and then they will just send you the rewards back to your account. So you can simply delegate from a ledger, which is the recommended way to do that. Then your funds are more secure, to a validator on the network. If you're not comfortable using ledgers and web wallets and things like that, you can also deposit into an exchange like Coinbase, Binance, or Kraken, and they can stake on your behalf as well. Yeah, let's see. Do you recommend using something like Kubernetes to manage your whole cluster of servers for staking architectures? This is a great question because this comes up a lot, but the reality is that Kubernetes is really designed for managing, I don't know if any of you have heard of this term of pets versus cattle, but the concept is like pets are animals that we love, we name them, we care for them. If they get sick, we bring them back to health. And then cattle are really, animals that are grown for food or for other purposes, and we don't give them names. They have numbers, and they're by and large expendable. And so the idea is that when we typically do like large-scale website operations, most of the web servers we're operating are considered cattle because they're like stateless web servers that are simply returning web pages or doing some function, and they don't hold state. State is all in your database. So they're pretty much expendable, and you can scale them out when you have more traffic. You can scale them back in when you have less traffic. So we treat most servers on the internet and in cloud environments like cattle. And then this allows us to automate everything and provision things very rapidly. But validators are actually more like pets. So pet servers might be something like a database server that has a lot of state, because validators essentially have to have a full copy of the digital ledger alongside them to operate, right? You have a full copy of the blockchain database, and it takes time to rehydrate that state. You also have to worry about, like, have I signed this block before? So validators are stateful, and they're much more like pets than cattle. So Kubernetes is really designed to run cattle type workloads very well, to run stateless containerized workloads. Although some people do run stateful workloads on Kubernetes, it's sort of an anti-pattern. And so I recommend actually not using Kubernetes for validators. There are a lot of places you can run Kubernetes for other infrastructure, for your monitoring infrastructure, for things like indexers and block explorers and all the other kind of tooling you're going to build around your validator as a service startup. You can use Kubernetes for that, and it's great. But the validators themselves are more like pets than cattle. And so I actually recommend you kind of treat those more like long-lived servers, and you don't run them on shared Kubernetes environments for security reasons as well, because in most Kubernetes environments, they have large shared namespace. And so if you had other, let's say web server type workloads running on your Kubernetes cluster, if someone compromised those, they might be able to get access to your validators as well. So I recommend kind of isolating the validators, running them on dedicated nodes in a dedicated account, and treating them more like pets than cattle. And then you should still have the configuration management automation. Infrastructure as code is very important, but these are long-living processes, not necessarily ephemeral processes. Is Ansible used in infra as code in any POS validator setups? Yes, Ansible is used very frequently. So a very good combination is like Terraform to provision all the underlying cloud resources like subnets and security groups and all of the networking constructs you need, as well as the cloud instances themselves, and then Ansible to provision the individual instance itself and like install all the software dependencies and ultimately pull in your software artifacts from your secure build pipeline. What software do you use for metrics and tracking the performance? So I use Grafana to kind of track most of the metrics. That's a great question. We've written some proprietary monitoring software for Tezos. And what we decided to do, typically when we're monitoring servers, we would monitor things like CPU, memory, network utilization, those typical attributes you would monitor. But what we really want to observe with validators is whether or not we're actually voting or participating in consensus. Because I could have a server that looks completely healthy, a validator looks healthy, the CPU load is not too high, we're not using too much memory, the network utilization is not high, but I'm not voting for some reason or another. Maybe one of my validator processes has died. And so what I really want is that observability signal showing me whether I'm voting or not. And so what we actually do is we run a monitoring solution that looks at the blockchain network itself and looks at whether my votes are being cast. Are my voting transactions appearing in the ledger? And if they're not appearing in the ledger, then I can fire an alert. So basically, we index the blockchain itself. We look for staking transactions where we look for whether we had the rights to produce a block at a specific height, and did we produce the block, or did we have the rights to vote at a specific height, and did we vote? And if we don't see those transactions, then I can basically alert on that. So I send those success or failure messages for voting to a time series database. I use CloudWatch metrics, but you could also use Prometheus, Grafana, whatever you want. And then from there, I set up alert thresholds. Like if I've missed more than X number of votes in an hour, then send an alert to PagerDuty and wake me up or something. So that's a good way to monitor. I highly recommend you develop like an observability solution that gives you visibility to whether you're actually voting or not. Let's see. Would it be useful at all to use a remote signer in a Docker container on the same machine as the validator? That's a great question. I don't think it's very useful, because if I can compromise the validator container itself, I could probably do a container exit and pivot to the remote signer container. So the Linux kernel surface area is just kind of too great to really avoid all the potential attacks that might allow me to exit a container. And so just trusting that the container itself will keep an attacker that compromises the application running in that container from accessing the remote signer running in another container on the same host is probably trusting too much. So a much better solution would be to just run the remote signer in a container on another host that's in an isolated account network. And that way your validator can send the request over the network. And if your validator is compromised, then it's not going to lead to a compromise of the remote signer container itself. What is the best way to protect DDoS for a small data center? Okay, so the best way I think for a small data center is run your remote signers and maybe even your validators in that data center and your HSMs and everything, but then run your edge or sentry nodes, your relay nodes in the public cloud, and then peer that small data center with your public cloud. You could even do this over a VPN if you don't want to pay for like a direct connect or private peering. But that way you're protecting your small data center footprint from the rest of the public internet. But you're running your relay nodes, your edge nodes, your sentry nodes in the cloud where they can absorb those volumetric attacks. But many of the smaller data centers even have, multiple gigabit internet connections, and they can kind of protect you from some of those attacks, just maybe not as good as a large cloud provider. Let's see, what else? How does your POS layering interact with other open layered efforts like MadeSafe? I'm sorry, I'm not really familiar with MadeSafe or XX Collective. All HSM has vulnerabilities though. Yeah, I think HSMs have varying degrees of security. There's FIPS compliance, but that's not always a silver bullet. And so I think it's important to have good physical security around where those HSMs reside. So that's, if you're using a cloud HSM, do the research, make sure your cloud provider has really good physical security. I think Amazon and Google do, but I'm not so sure about other providers. If you're using a physical colo, make sure they have really good physical security controls and that no unauthorized people can get access to your cage or to your servers. So I think it's important to kind of recognize that a very well-resourced attacker that has physical access to your HSM for a period of time might be able to extract key material still. So you can't always trust that the HSM itself is the silver bullet to solve all problems. Let's see. For Tezos specifically, by remote signer inspect the payload, you mean checking the magic byte? Yes. So the magic byte, let me kind of skip back to this on the presentation. The magic byte is byte 0 here. And this byte will always be a 01 or a 02 if it's a block. 01 is for a block production message, or 02 is for a vote or an endorsement on another block. So if this is a 01 or a 02, we know it's a staking transaction. So what we need to inspect is the block height, and we need to make sure we haven't signed this height before. So that's the double signing protection. If it's a 03, that is used for all other types of operations. So that's used for transfers or sends. It's also used for ballots or governance transactions. And so if it's a type 3, we actually need to look and inspect the payload and say, is this a ballot or a vote governance transaction? If so, I should sign it. And if it's a send, then we want to really look at like who's the recipient of the funds, the destination address. Should I be sending funds to them? Are they whitelisted? And what is the, have I reached my rate limit of maximum funds per day or per cycle that I should send to this address? Let's see. Yep, with all the talk of HSMs, it should be noted that they are all subject to vulnerabilities. It is absolutely fair to say some are more secure than others, though. Yep, that is true. I completely agree with that. I'm not Ether savvy lately. What are its properties? So Ethereum is a pure proof of stake network when it launches Casper. So that represents additional challenges in the sense that you can't delegate your stake to a validator, where like you can in Cosmos or Tezos. So that means that essentially Ethereum wants to have thousands of validators online, and each one has no more than 32 ETH staked to it. Ethereum also has a dual account key strategy where you have a spending key that's used to like transfer funds, and then you have a consensus key that's used for validators to vote. And so the consensus key has a different signing curve. It's like a BLS curve than the normal spending key, which is like your normal Bitcoin Ethereum K curve. But with Ethereum, it's going to create a lot of challenges because you can imagine large validator as a service companies are going to have to run hundreds or potentially thousands of validator nodes. So it becomes a distributed systems problem. And it's also going to be interesting to see if Ethereum is able to really have real decentralization or if it will be more like fake decentralization. And what I mean by that is if there are thousands of validators on the Ethereum network, but they're all running inside a few large validator as a service companies, then we haven't really decentralized the network, because it might look decentralized on the surface, but if you compromise one of those large validators and you can cause all other validators to be compromised, then you've essentially attacked a large percentage of the network by attacking a single provider. So I think there's a real risk with Ethereum that we end up with sort of a fake decentralization where it looks decentralized on the surface and it's not really decentralized underneath the covers. And so with delegated proof of stake models, you don't have as much of that risk in the sense that the delegation is visible on chain, and you know how much stake is behind every validator as a service provider. Now, validators as service providers could have multiple validators, and they could have Sybil validators and other types of attacks. So there might be some fake decentralization even in delegated networks, but it's more visible because all the delegations happen on chain. So you know who is delegated where and how much stake their validator has. Yeah, I would like to see someone point out a vulnerability with UBHSM too. As far as I know, it hasn't happened yet. Yeah, so I think this is a great call out in the sense that if you just take a UBHSM and plug it into your validator node, and then you have a remote signer running as another process on that, right on your validator, maybe using Tendermint KMS or something, like you're still at risk, because if someone hacks your validator, they don't actually have to talk to Tendermint KMS. They can just talk to the HSM itself and get a signature, and they can double sign, or maybe they can even export your private key material. So this is a big reason why you should always put the HSM in another system besides your validator node itself. So even if UBHSM is perfectly secure and has no vulnerabilities, someone that gets on the validator, if it's in the same box, has the keys to the kingdom, literally. Let's see, what else? Yeah, by the way, thanks for the comment, Brian, about the Tezos signature bytes map for the first time. I want to thank Rob Widoff at Polychain Labs for creating this. This was really useful. Our initial version of the remote signer did some safety checks in terms of we checked the magic byte and we checked the block height that we were signing, but we didn't have all of these cool features like address whitelisting for rewards payments to your delegators, or governance vote whitelisting, which Rob added. And he was able to do it by kind of figuring out the transaction payload format. And so I want to thank Rob for providing this cool diagram for us. Yeah, I kind of agree with you, Ian, that I think it would be interesting if Ethereum allowed staking of stakes on nodes, so potentially allow large validators to combine multiple or delegate basically, or combine stake into larger stake pools, because then at least the centralization or decentralization factor would be visible, and you could at least trust that what you think is decentralized is really decentralized. Yeah, that's a really good point, Eddie. I actually like that idea about not allow O3 at all, set up a separate signer standard, start on demand for sends, no matter address whitelisting. So on the Tezos Foundation validators, we actually don't have this address whitelisting and sending feature enabled, because we never send funds out of those validators. It just stays there for this security deposits and bonds. So I actually don't have that address whitelisting feature, but I do need to whitelist votes. So every quarter when the Tezos Foundation votes pass to remain impartial on the governance process, I start a separate set of remote signers that's just used to sign those vote transactions, that is authorize those types of transactions only. So I really like that idea. So,
yeah, we have time for about one more question.
Oh, okay, cool. Any final questions? I don't really see anything compelling in the chat channel, but this was really fun, guys. Thanks for all the great questions and interaction.
And thank you, Luke. And if everyone can just he's given us so much knowledge just now, and if everyone could just, oh, I love the cats.
The kitties are restless.
That's amazing. Yeah, just thank Luke in the chat. He's been a huge help, and keep the questions coming, please. It's been great thus far, and Shinju is going to introduce the next panel. So thanks again, Luke, and we will see you next time.
Thanks.
Bye.